In this video, we are going to be talking about dipoles, bond polarity, polarity within molecules, and how to determine whether a molecule is polar versus nonpolar. So if we take a look at this image, we have the word dipole here. Di means two, pole means sides. So if you end up having a pole toward one side of a molecule, you will end up with a dipole molecule. This is going to be indicated by either a partial positive and partial negative sign or one of these arrows that represent a dipole moment. Now, in order to figure out if you're going to end up with a partially positive and partially negative side of a molecule or a bond, we have to review electronegativities and bond polarity. So you are going to have to refer to your periodic table on this. Recall that electronegativity is basically how attractive a nucleus is to electrons within a molecule. So as you move across a period on the periodic table, electronegativity increases. These atoms on the right-hand side are much more attractive than the atoms on the left-hand side. Electronegativity decreases as you go down because there's more energy levels, the nuclear charge isn't felt as much, so it is not attractive to atoms within a chemical bond because of all those layers of energy levels shielding the nuclear charge. So again, electronegativity increases as you go across a period, and it will increase as you go up a group. So the most electronegative elements on the table are in the upper right-hand corner. Now, when we're thinking about polarity, we do have to think about those electronegativity differences between atoms in a molecule. So if there is a polar covalent bond, what that means is that on one side of the molecule, those electrons are going to be more attracted toward one side of the molecule versus another side of the molecule. If something is nonpolar, it means that there's an equal attraction among the elements within the entire molecule. And we're going to look at instances of both these things. So in order to figure out if a molecule is polar versus nonpolar, we do have to consider the shape of the molecule. The shape does make a difference. So I have a couple examples that I'm going to go through with you in a minute. Another thing we're going to look at is whether or not it has polar bonds and whether or not those polar bonds will cancel versus not cancel. The first one we're going to look at is water. Here's the Lewis dot structure for water. Now, its shape is very, very important here because if we don't draw these unshared pairs on the same side of the oxygen, it appears as if water is linear. So even though this Lewis dot structure is correct, it would be very difficult to figure out the polarity of water if we don't recognize, oh, there are unshared pairs on the central atom. So really what I need to do is I need to bend one of the hydrogens and draw my oxygen on the same side, so that then we are able to determine that this is going to end up being a polar molecule. So I'm going to walk you through that now. So here we have unshared pairs on the central atom. And the first step to consider when we're figuring out if a molecule is polar or nonpolar, we need to ask ourselves if the bonds are polar or nonpolar. Basically, anything that isn't a carbon to hydrogen bond is going to be a polar bond. So if we take a look at this, it is not a bond between carbon and hydrogen, so these are polar bonds, and it could end up being a polar molecule. So the next thing we ask ourselves is the molecule symmetrical or asymmetrical? Where this molecule, we could divide it this way, And it is the same on both sides, but the thing is that it is not the same if we divide it this way. We have oxygen on one side, we have these hydrogens on this other side. Because of that, this molecule will end up being polar. So when we finally determine that a molecule is polar, we do want to draw that dipole in it. And you can either represent this with an arrow or the partially positive, partially negative symbols. So in order to figure out which direction our electrons want to go, remember the electrons want to go toward the most electronegative element involved in the structure. So we're comparing oxygen and hydrogen here, and everything is more electronegative than hydrogen. So everything wants to go toward this oxygen. If we were drawing an arrow, we would draw the arrow up through the oxygen and a little plus sign on the other side. If you're drawing your partial positive, partial negative symbols, you would just on the oxygen side put that little S symbol. Whoop, sorry, messed that up. You'd put the little S symbol with a minus, and then on the hydrogen sides, those become partially positive. I will leave it up to you what you prefer to do, whether you use the partially positive versus negative, or you draw your dipole arrow. The next example we are going to look at is CO2. And this is another example where it's really important to draw the compounds properly. So for instance, sometimes people draw CO2 like this. And the symbol here is correct. You have each of these oxygens are happy with 8 valence electrons, and the carbon is happy with 2, 4, 6, 8. But you notice that the central atom does not have any unshared pairs. So even though I drew this bent, it is not bent. It is actually linear. So feel free to erase if you do this and redraw it so that you're actually showing a linear compound. It will help you to determine the polarity. So here we are. So we're going to go back, ask ourselves, are there polar bonds? Well, there aren't any carbon-hydrogen bonds, so these are definitely polar bonds in the molecule. And then we need to determine, all right, well, do the polar bonds cancel, or is one side of the molecule more electronegative than the other side of the molecule? And if we take a look, this carbon is surrounded by 2 oxygens. If we look at our periodic table, carbon compared to oxygen, oxygen's more to the right-hand side, so oxygen's the most electronegative element in this compound. But the thing is that there's oxygens on both sides. So there's a pole out to each of the oxygens. So you can't say that one of the oxygens is more electronegative than another, or one is going to become more negative than the other one with the way those electrons are flowing. Because there's an equal pole out to each side, those poles actually cancel, and this is a non-polar molecule. So if you can't determine which way you would draw one arrow, and they're both going out to all sides, or if you can quickly see that the compound is symmetrical on all sides, then it is a non-polar molecule. The next example we're going to look at is carbon tetrachloride. So we have a carbon with 4 chlorines surrounding it. Right away, hopefully you notice that this is a nonpolar molecule. I see that there are 4 chlorines surrounding this carbon, so it's the same exact on all sides. So even if the bonds are polar, there's an equal pole to all sides, and they cancel. So this particular molecule is non-polar. A similar example to where we might think it looks symmetrical, but it really is not, is CH2Cl. So here we have carbon surrounded with hydrogens. A carbon to hydrogen bond is a nonpolar bond, But here we have carbon to chlorine. So these are polar bonds. Even though there are 4 things around the carbon, it is not symmetrical because hydrogen is all the way on the left-hand side of the table and the chlorine is all the way on the right. Chlorine is much more electronegative than hydrogen and then that carbon atom. So this molecule is not symmetrical on all sides because there are different elements on each side of the molecule. And chlorine is our most electronegative, so it is polar, and we would draw our dipole through those chlorines. The next one we're going to do is CH2O. Here we have another carbon to hydrogen bond. Those are nonpolar bonds, but we do also have this carbon to oxygen bond, which is a polar bond. Where if we divided the molecule up this way, it does seem symmetrical, but this way it is not. So the oxygen is on one side of the molecule, the hydrogens are on another. Oxygen is the most electronegative because when we take a look at our periodic table, it is further to the right than the carbon and also than the hydrogen. So it is a polar molecule and everything wants to go toward that oxygen. So we draw our dipole that direction. This side becomes partially negative, this side is partially positive, and this is polar. The last one that we're going to do is a carbonate. Here we have 3 things connected to the central atom. Hopefully you realize right away that those 3 things are all the same, and therefore this is a nonpolar molecule, even though there are polar bonds. It's nonpolar because it's the same on all sides. You can't say that one oxygen is more electronegative than another because all oxygen atoms have the same electronegativity. So even though there are polar bonds, those polar bonds cancel, and this is a nonpolar molecule.